So in the lecture recordings, we talked about the Wronskian as a way of understanding a list of functions and trying to decide if they're independent or dependent. Weirdly, the Wronskian doesn't work backwards, right? It's a one-directional result. And what's subtle is why. So if you look at the argument for why the Wronskian works as it does, it really looks like at a glance that all of the steps in that argument are reversible, but they're not. And it's subtle, but one of them is not quite reversible. So that's what I want to talk about here. Let's go through the point. So here it is. This is the specific point that does not work the other way. Why does the Wronskian not work the other way? It's this bit right here. So in the original argument that we made to derive the Wronskian in the first place, we found ourselves with a matrix being multiplied by some coefficients and getting 0. And specifically, these coefficients, right, were not just any old numbers. These were constants. They had to be constants because they came from a relation, and a relation between functions. And again, originally we were looking at a relation between functions. The coefficients have to be constants. Okay, so anyway, that being the case, if you have a non-trivial null space, if you have a vector in this, if you have a homogeneous solution, however you want to say it, then we know that the determinant of that matrix is equal to 0. And well, this is true for all values of x, and so the determinant is equal to 0 for all values of x. Okay, all right, and then we reason further from there. So why wouldn't this just turn around backwards is what we're sort of faced with trying to understand. All right, so the problem is that it kind of does, but not quite. So if you look at any single value of x, for a single value of x, yes, it is true that that matrix having determinant 0, there will be some numbers, c, that make this equation work. Sure. But what is not clear is that whichever x you look at, that you will get the same values of x, the same values of c for all values of x. In other words, these would need to be constants, independent of which x you're looking at. And it's we're going to see is that that's not always the case. Certainly that does not follow. Certainly it does not immediately follow from here. Does not follow that you will always get the same coefficients. And that's what we would need in order for this to be a relation. Okay. All right. So we talked about that in class. What I want to do now is show you an explicit example of that happening and where you can even kind of geometrically see why the constants are not why the coefficients are not constants. Okay, so here is that explicit example. We're going to look at a couple of functions here. The first function is x squared. Oh, I can do better than that. Let's see here. Here we go. And then the second function is a little bit hard to write down. I'm writing in a signum of x times x squared. Signum is just a fancy way of saying, well, plus or minus, depending on whether x is positive or negative. That's all it is. So what we have here, this function g of x is x squared when x is positive, but it's negative x squared when x is negative. Okay, a little bit of a weird function. Okay, so claim this is our counterexample. Now, keep in mind what we're looking for. We're looking for our Wronskian argument failing. And so what we're going to find is that the Wronskian is 0 everywhere. We're going to see that very quickly here. And if the Wronskian were to be a reversible argument, then we would need to conclude that that means that these functions are dependent. But we're going to find that they're independent. Okay, so anyway, let's see the calculation. We do have to do this calculation in different parts. We have to do the calculation sort of once over here, where x is negative, where we have one formula for what g is. And then I have to make a different argument over here when x is positive, Again, we have a different formula for what G is. And technically, we do have to make yet a third argument where X is equal to 0. The reason we have to make a different argument there is that it is not quite as easy to compute the derivative of this weirdo function here when X is equal to 0. So anyway, we'll call it 3 separate arguments. And here go those arguments. Notice in each case, we just write down exactly what the formula is. Here's F, and below are its derivatives. Here's G. Now, again, keep in mind, we are looking over here where X is negative. So G is negative X squared. Okay. And so for these values of X, compute. There's the Wronskian, it's 0. Okay. All right. When X is positive, for these values of X over here, well, then we just have this is our formula for G. Of course, we have the same formula for F. Looking at those values, compute the Wronskian. Easy to do. And again, we get 0. At 0 itself, the values of the function are clearly just 0. Both of them are. So in some sense, it kind of doesn't really matter what's in the second row. But at the same time, we can compute those. The derivative of X squared is pretty easily seen to be 0. This one down here, how do we take the derivative at 0 of this weird function here? That's an exercise in Calc 1. You have to go back to the definition of a derivative, and it's just a matter of doing it. It's not that big of a deal. It's a nice exercise. If you're looking for a good exercise in Calc 1, feel free to do that. But I'm going to just assert here the result, that derivative is 0. Anyway, nice agreement. The Wronskian still 0. So the Wronskian is 0 everywhere. If the Wronskian were a reversible tool, then we would conclude that these are dependent. But they are not dependent. And let's see how that works. How do we know that they're not dependent? Well, let's think about how would we relate these functions for different values of X. And I'm going to have to zoom out here so we can see better. Again, here are our two functions. Let's look over here where X is negative first. How do I relate these two functions where X is negative? Well, they're negatives of each other. That means that they add up to 0. In other words, the coefficients 1 and 1 are what you might call the candidate relation. That's the relation for those values of X anyway. These coefficients are 1 and 1. You see it in the functions themselves. However, you come over here to where X is positive. For these values of X, F and G are the same. That means that it is their difference that is 0. That means that the coefficients are 1 and -1. That says that this C vector is 1, -1, not 1, +1. So you notice then for different values of X, whether X is negative or X is positive, you get different C's. So going back up to here, you don't get constant coefficients, and therefore there is actually no actual relation. And that's what we really needed. We needed to have a relation between the functions. So this is the example. The reason I like this example is because you can, again, looking at the graphs of these functions, you can explicitly see it happening. You can see how there is a relation between F and G over here, right? They're the same. And there is a relation between F and G over here. They're negatives of each other in both cases, whether you're looking at X on the left or X on the right. One is a multiple of the other. But which multiple changes? And so therefore, as a whole, for all values of X, can I view either one of these as being a constant scalar multiple of the other? No, we cannot. Okay. All right, so I think it's a nice visually satisfying example. And this, again, this gives us our counterexample. The list is independent, even though the Wronskian was easily seen to be 0. Okay, so you cannot turn around the Wronskian argument.